Hello, welcome back to Organic Chemistry 2341. And for those 70 people who didn't show up for class, you get to watch it here. Yay. Anyway, so there, got it jabbing me. So we have our new module today, and I like module 6 because it's where we get to do kind of real chemistry. You know, in chapter 1, we learned about electrons and that they formed bonds and that they formed polar bonds. And those polar bonds are going to be the more reactive ones. And we're going to play with that a little bit in this one. And then we learned about acids and bases and Lewis acids and bases, which actually is the same as our electrophiles and our nucleophiles. And we'll talk about that today as well. Then we learned about nomenclature. And of course, you have to name things once you do it, right? And so we have to classify things. And then we started adding a little bit more onto the level of complexity by doing our stereochemistry, regiochemistry. We needed to know regiochemistry because our reactions can be regiospecific, make certain isomers and make a mixture of isomers. So we needed to know that to get here. So we have all this foundational information to get us to this chapter, and now we can actually start playing with the real chemistry, okay? So that's why I like this chemistry, this chapter in particular, and we get to start talking about substitution reactions. But before we talk about substitution reactions, let me go ahead and share my screen. This chapter is broken into, okay, hang on, let me put the zoom up here. The zoom screen is in there. All right, everybody's in now. Okay, so everybody can see my screen, right? The module 6.1 slides, right? All right, great. So what we're going to talk about is the different types of reactions that we're going to do throughout the rest of the year, actually both semesters of there, but we're going to talk about the substitution reactions, particularly in this module. Okay, so there are a bunch of different kinds of reactions we have here in organic chemistry. The first time I'm going to talk about substitution reactions is in this chapter, and then we'll talk about elimination reactions in the next chapter. But the basic idea in a substitution reaction is it does what it says. You're going to take one thing off the molecule and add one thing onto the molecule in that same place. So it's substituting another group. Usually we're substituting alkyl halides or halogens because they have very polar bonds, very reactive bonds, and so we can displace them with other things, okay? And there's a specific mechanism we're going to use with this, and it's called the nucleophilic substitution reaction. So we're going to have something that has a negative charge looking for a positive charge or partially positive charge, and it's going to displace something off of the molecule, giving us the substitution there. So we're going to look for the substitution reactions, and we usually have a big S for those. And nucleophilic, we usually have an N for those, okay? So that's a substitution reaction. The next kind of reaction we have, and we'll talk about this in chapter 7, is our elimination reaction. In elimination reactions, we lose two groups. Sometimes it's just two hydrogens, sometimes it's a hydrogen and a halogen, sometimes it's two halogens, okay? And when we do that, we go from having sp3 hybridized carbons down to sp2 hybridized carbons, and we usually form a double bond, okay? So that's our elimination reaction. So we have a substitution reaction. Now we have an elimination reaction. Well, in that chapter 7, we're also going to learn about addition reactions. Now that you have that double bond is electron rich. And so it is the nucleophile, and it will reach out and attack things and have it add across that double bond. So when you add across that double bond, you're going to get one thing on one carbon, one thing on the other carbon, hence addition reaction, okay? We'll do a lot about the mechanisms of those next chapter. The other thing we can have happen, and we're not going to do this specifically this semester, we're going to actually do it next semester, is what we call a rearrangement reaction. In a rearrangement reaction, we can have something happen to where it changes its conformation, but all the attachments are still there. It's just we've changed our reorganization. So sometimes you can have a hydrogen or a methyl group move around the molecule. Sometimes it just does what this does, and it goes through a cis-trans isomerization. Remember that double bond's rigid, and so it can't rotate without some kind of force acting on it. In this case, we're using an acid to kind of break that double bond for a little while and then allow the molecule to rotate around its sigma bond and then reform that double bond. Okay, so that's what we call a rearrangement reaction. Okay, and those happen a lot when we start talking about carbocations. So write that down, carbocations rearrangement. All right. So another thing we have is what we call bond cleavage, okay? So for example, that's how we can form a carbocation, is having a bond cleave, but there's two ways to do it. The first way is we can have what we call heterolytic cleavage. That means where the two separating parts have different amounts of electrons. That one took both of the electrons from the sigma bond, the other one had no electrons left. So that's heterolytic because we usually end up with a negative charge and a positive charge. The other way to do it is to have what we call homolytic cleavage. In homolytic cleavage, that sigma bond is broken such that each of the leaving parties has one of the electrons, and therefore they each have a radical, and that is a homolytic cleavage. We'll talk about that in chapter 10. Okay, but so most of the time we're going to have this heterolytic cleavage in most of our substitution and or elimination reactions. Okay, now one important thing to know is that bond breaking is endothermic, and we're going to learn that endothermic means it absorbs heat to do so. That means that bond forming is usually exothermic, or gives off heat. Okay, and we'll talk about thermodynamics in this chapter. Okay. Now, the next thing we have, if we can break a bond, we can also form bonds, okay? So we can do it two ways. Again, we can do it heterogenically. Heterogenically means we have a positive charge and a negative charge. That negative charge turns into that new sigma bond, giving us our new bond. And these reactions, this bond forming reaction is exothermic, gives off heat, because we lose the potential energy from the two other components, and it's being lost in the formation of that new bond. We can also do that with those single electrons on each one. It's called a radical-radical coupling, and each electron contributes into making that new sigma bond. And that's what we call a homogenic reaction, because each one is bringing one electron to form that new sigma bond. All right. And questions on the types of bonds we're going to be looking at. Okay. So the heterogenic bond we're going to be seeing in this chapter and in the next chapter. The homogenic bonds we'll be looking at specifically in chapter 10 when we do radicals. All right. So that's what we have to look forward to for this semester and next semester, looking at all the ways that we have these things. Notice there's not that many types of reactions. All these reactions kind of fall into this general group of substitution, elimination, addition, bond breaking, and bond forming, so, and rearrangement. So they all fall into that one way or another. But I just said that those forming bonds is exothermic and breaking bonds is endothermic. So let's talk about thermodynamics, okay? Thermodynamics, don't be scared. We don't have to do any calculations. Thermodynamics is just giving us a framework on why the reaction is progressing the way it does. And if we have competing reactions, which product is going to be favored? Is it thermodynamically favored or kinetically favored? And so we're going to talk about that. So thermodynamics. Question? Oh, no, okay. So thermodynamics is basically the difference in energy between the starting materials and the products, okay? So we're looking at the difference in energy. And now in physical chemistry, there's a whole bunch of thermodynamics, but it all kind of boils down to the idea is when we use it in organic chemistry, we're looking at the difference in that energy between the products. Now, this, I have it stated as free energy, and we're going to talk about Gibbs free energy first, but then for the most of the time, we're going to talk about enthalpy, which is basically the heat of the reaction. But Gibbs free energy and enthalpy are related, and I'll show you that equation. What we think about is if you have more free energy, you have more energy that can be stored as potential energy in your molecule. And if you have less Gibbs free energy, you have less of that potential energy stored in your molecule. So think about it as that kind of way to consider these things. And if the reaction of is converted to a product, there's always a difference in energy. You're either going to have more Gibbs free energy at the end of the reaction or less energy, and those have different types of reactions, and we're going to talk about those specifically. So I love these little diagrams. These are called reaction diagrams or reaction coordinate diagrams. It tells us what's happening in the presence of, as a function of energy as the reaction progresses, okay? So we want to get very familiar with these because it really tells us a lot about what we're doing here. So we have our free energy scale here, and sometimes it's going to be enthalpy, the change in enthalpy. Sometimes it's going to be the change in free energy right here. But the idea here is that you have some amount of energy stored in the bonds you already have, okay? And they're happy. They are going to need some other force, some other energy in the system to get those bonds to break, right? To change to a different type of bond. So we have a rise in energy to go to a transition state, okay? And so it's starting to break the bonds it already has and form new bonds. And then we have a new products formed down here, okay? And notice that the energy difference between the new products formed and the starting materials is what we call the change in Gibbs free energy. And in the case of if there's a positive change in Gibbs free energy, meaning that your energy here is less than before, let's say, I'm sorry, if you have a negative change, Gibbs free energy is less than 0. So if your Gibbs free energy is lower at the end of the reaction than it was at the beginning of the reaction, we call that exergonic, okay? Meaning that it's given off this much Gibbs free energy going from the starting materials to the products. This is free energy that's given away from the system. Is bond forming and breaking occurring at the peak? We'll talk in more detail on that, but I just wanted to show you that there's this peak, this transition state we're going to talk about. Okay. So the basic idea here of the energy diagrams is we're looking at the difference between the starting materials and the products and this height of this peak. That's going to play a really good, a really big role in the thermodynamics of our system. Okay. So let's talk about that relationship between the equilibrium constant and the Gibbs free energy. Okay. So every reaction is to some extent, even if it's tiny, tends to fall in an equilibrium, okay? So what we mean by that is that if we divide the concentration of all the products by the concentration of all the reactants, there's going to be some place where you're going to have maybe a little bit of product or a lot of product and a little bit of reactant or a lot of reactant. And wherever it stops and it balances out so those concentrations don't change, that's what we call our equilibrium constant here. Okay. Now, how does equilibrium constant relate to Gibbs free energy? Well, we can take the natural log of our equilibrium constant, because this is going to be a really big number. This turns it into a much smaller number, times its temperature in Kelvin, times the ideal gas law constant, and that gives you the Gibbs free energy of the reaction. Okay, so we can directly correlate that Gibbs free energy of the reaction or that change in Gibbs free energy of the reaction by which way the equilibrium is going. If we're going toward reactants going down, then that we're going to have a very small change in Gibbs free energy. If we're going more toward products, we're going to have a bigger change in Gibbs free energy. Okay, so by measuring the concentration of the different things in reactions, we get this equilibrium constant, and from that equilibrium constant, we can actually calculate the total change in the Gibbs free energy. Okay. So how does this relate to enthalpy? Because I said enthalpy is what we're going to use most of the time. So enthalpy is really talking about the heat and or bond energy of the system, okay? But they're related by entropy and temperature, okay? So the change in Gibbs free energy is equal to the change in the enthalpy minus the temperature in Kelvin and the change in entropy of a system, okay? So what's entropy? Okay, if you have one thing, you have a certain amount of entropy. If you break it into two things, you now have more entropy, because entropy is more disorder, okay? So entropy is just, if you start with 5 starting materials and you go to 1 starting material, you're going down in entropy, right? If you started with one thing and you break it up into 5 things, you're going up in entropy. Okay. So a lot of times the change in entropy, you're going from 2 starting materials to 2 products, and so the enthalpy really doesn't change that much. And the temperature in Kelvin really doesn't start approaching, start really affecting the math very much until it's like 700 or 800 Kelvin. It's got to be very high temperature before it starts making the Gibbs free energy and the enthalpy not the same. They're very close together. They're really proportional based on that little thing, but there has to be a big change in the temperature and enthalpy. I'm sorry, the temperature and the entropy before you start worrying about the Gibbs free energy being different than the enthalpy. Okay, so the general rule here is that if the delta H is negative, right? So you're losing stored enthalpy in the reaction, it gives off heat, okay? And if a reaction gives off heat, it tends to be spontaneous, okay? So if you have a negative enthalpy, it tends to go all by itself, okay? You don't have to drive it forward, okay? And if the disorder if you go from one product to two, that's also going to be positive, and that will also drive your reaction to be spontaneous. So breaking a large molecule up into smaller molecules will have a positive entropy or change in disorder. Okay. A spontaneous reaction does not occur if the process has an increase in enthalpy or is endothermic, meaning you have to push a whole bunch of energy into it, and then the energy of the products is higher than the energy of the starting materials. That's endothermic. You're adding heat, you're adding potential energy to your molecules. And when you decrease order, when you go from 5 molecules to 1, that's a negative entropy element. And so those reactions tend to not occur spontaneously. Okay. Now, there is a middle ground where one will change and the other won't. And so enthalpy is a lot more important at low temperatures. But once we get to very high temperatures, the entropy and temperature component plays a bigger and bigger role. Okay, so that's why we can typically just look at the enthalpy reaction and know whether it's going to be spontaneous or not. Okay. Now, when the entropy is greater than 0, meaning you get more things, the reaction tends to be favored because of that entropy. Okay. So those are all just general guidelines, but let's actually put them to use here. Okay, so if a single starting material forms 2 products, you have a positive increase in entropy, right? You have more disorder, okay? If a cyclic molecule, because it has limited range of what it can do, breaks open, now you have more disorder and you have a positive entropy, okay? When your entropy is less than 0, it's not favored. So if you're going with bigger, 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 unless there's a large negative enthalpy value, unless you're giving off a lot of heat, okay? So if you can take 5 molecules, turn them all into 1 and have the product be a much lower potential energy than the starting material, it'll overcome that entropy change, okay? So we have to look at both, the change in the enthalpy or the free energy and the entropy at the same time. So conditions that favor reactants tend to be ones that have an equilibrium constant less than 1, because the reactants are on the bottom, the products are on the top, right? And so as those get bigger, you're going to have a positive change in enthalpy, a positive change in Gibbs free energy, and a negative change in entropy, because you're going to your products, okay? When you favor, you favor the reactants. When the reaction is favoring the products, i.e. spontaneous, the equilibrium constant is greater than 1. The enthalpy is less than 0, meaning it's negative. You're giving off heat. In this first one right here, you're actually absorbing heat to make it happen. Here, you're giving off heat to make it happen. Here, you're giving away Gibbs free energy, and your entropy is positive. So if you're giving off heat and you're creating more entropy, you're more likely to have the reaction go to products. Okay, so, that's a lot to remember, but if we look at our energy diagram, it tells us all that, okay? So that's why I like the energy diagram, because it really tells you all the things that are happening here. So I'm going to show you two different energy diagrams, and we're going to talk about this one on the left first. Okay. So on the energy diagram, we're looking at, this is the free energy. It could also be enthalpy. Okay. And we're going to start somewhere because, you had two chemicals in a jars and you put them together. Okay. So that's your starting energy. Okay. So once you do that, and if there's enough energy in the heat of the room to make the reaction go, it's spontaneous. That energy required to get to this transition state is this free energy of activation. Sometimes it's called activation energy, which is EA or EAC. Sometimes it's the free energy of activation. The point is that there has to be some energy absorbed to get your reactants to get to a transition state. Now, this is where William's question comes in. In the transition state, we are forming a bond and breaking a bond at the exact same time. Okay. Okay, what that means is that transition state is a mythical or ethereal state where you're having one bond form and one bond break. You cannot isolate that. You cannot isolate that. It is just happening like it's like a spectrum. One bond is forming, one bond is breaking, and then boom, you now have products. Okay, so that is our transition state here. And then once you have your transition state, the energy that was absorbed to make this activation energy and any change in the free energy of the products is lost here. So in the case of heat, we would lose heat in the reaction would heat up, and our products now have this much free energy. So that difference in the energy from starting materials to products is our free energy change. And again, if we're giving off energy, we're taking away that potential stored energy and giving it off. It's spontaneous reaction and it goes forward. Notice that we are not changing our entropy. We had two components at the beginning and we had two components at the end, and we're not heating it with a huge amount of heat. So our enthalpy and our free energy are approximately the same. Okay, so we have two products here, so entropy did not change. Okay, let's take another example that's a little different here. And in this case here, oh, by the way, this is an exothermic or exergonic reaction because Gibbs free energy and or heat was given off. Okay. In this state here, we are looking at it a different way. We're starting with our reactants that had very little potential energy, and our products have a lot of potential energy. Okay, so that change in there tells us a lot about the reaction. First of all, it tells us that this is an endergonic reaction. We are absorbing free energy. We are storing it in that molecule. Okay, so we have a negative. We are losing free energy by storing it in the molecule. In addition, we are losing heat. We are absorbing heat to make that higher energy molecule. Those bonds have more energy in them. Therefore, they had to absorb heat to get there. Okay, so whenever your reactants are lower than your product, we have an endergonic, meaning you lost free energy because it's being stored in the bonds, or endothermic, meaning it's absorbing heat to make those new higher energy bonds. Okay, but you still had to have your activation energy. So you had to add energy to the system to get it to the transition state. And once it got to that transition state, it formed those new products. Okay. So in most cases, this can happen in equilibrium reactions where you have it. And in most cases, if you leave it long enough, it's going to kind of blend out to where it'll go to the more stable or lowest potential energy products. But you can force these things to store extra energy, usually by using some kind of reagent that allows you to store more energy in the products than you started with your reactants. And that's how we get some of our higher energy chemicals, or our very reactive chemicals, by forcing them uphill in the energy barrier. Okay. Okay, so important things about these. Yes, that is true. The energy that we're storing in the bonds is analogous to the free energy change in the endergonic diagram. That is true. So the important parts about these are the shape of the diagram, okay? Where are the starting materials and where are the products? The height of that activation energy is very important. So those are the things we're going to look for in each and every reaction to show whether it's going to go forward, whether it's going to be spontaneous, or whether it's going to be difficult to produce, or where the equilibrium might lie based on the energy of the products. Okay, so let's take a one-step reaction just to show a simple energy diagram. In a one-step reaction where you come to your transition state and form your products, you have one hum, okay? So, for example, this is a substitution reaction. We are substituting the bromine here with the OH. Okay, so this is a substitution reaction, and this OH has a negative charge, meaning it's a nucleophile. It's a Lewis base. It wants to use those electrons to make a new bond. Okay, so we have to go, there has to be some energy required to get the molecules moving fast enough and hitting each other. They have to hit each other or get close enough to start forming and breaking a bond to get to that transition state. So that's this activation energy. Sometimes it's just heat from motion and the particles are moving around. Sometimes it can be induced by like light to vibrate a bond to make it more reactive, okay? But it needs energy to get to that transition state. And so we're forming this new bond with these electrons here. The electrons that were the old bond are now going to end up on the leaving group, in this case, the bromine right here. And our products are at a lower potential energy than they were in our starting material. So that is the change in enthalpy, which means it's an exothermic reaction. Okay. So that's the driving force for this. You're taking stored energy from one set of bonds, breaking those, and you're storing less energy in the new bonds formed. Okay? So that's a one-step reaction. But of course, they're not all one-step reactions, right? Sometimes you form a very reactive species, but you can isolate it. When you form a reactive species that you can isolate, we call that an intermediate, okay? Meaning it's a unique chemical species that you can see either by spectroscopy or isolate or store in a bottle, right? But it's still very reactive. It has more potential energy than the starting materials, okay? So it's going to have to then do a second reaction to take it from that reactive intermediate to the final products. And so we call this a two-step reaction. In this case here, we're going to do one of those reaction types we have. We're going to break a bond. Our first step is giving it enough energy to get to its first transition state and break this bond. Once it breaks that bond, the bromine goes away as the bromine ion. And in this case, we have a positive charge on carbon, our carbocation. It's a very reactive species. It's not going to sit around for long. All that has to happen is something needs to come around that is a nucleophile, something to make electrons to make a bond. And it'll go through that transition state again. Usually it's a lower activation energy because you have a very reactive species. And then you cascade down to products. And if the products are less than the starting material, the reaction is exothermic. Okay, three things that are important here. We have two different transition states right here because you have different things reacting. You had the T-butyl bromide here reacting to give you the intermediate, and then you have the intermediate reacting to give you the products, okay? So we have two different transition states. We have two different activation energies, okay? And the third most important thing here is the intermediate is higher in energy than your starting materials, okay? Almost always is your intermediate higher than your starting materials. And then your intermediate is usually higher in energy than your products as well. Okay, so that's how to dissect a reaction diagram to tell you what's happening when in the reaction as it progresses. Okay, so this is the thermodynamics of a reaction. Now let's talk about the kinetics, and there's about 5 things that affect kinetics in reactions, okay? So really, the kinetic is just the speed or rate of the reaction, okay? And you can usually estimate it by looking at the height of the energy barrier, that activation energy, which will in our diagram. And usually if you have 2 activation energies, the first one is usually the highest one and usually is the slowest one. And we'll talk about the slow and high, okay? But the higher the barrier, the slower the reaction. The lower the barrier, the faster the reaction, okay? And there's a reason for this. The reason for this is that you have to have, the higher the energy barrier is, the fewer molecules are going to be going fast enough, being close enough, and have enough energy to make your transition state. That's why it runs slower. You have fewer molecules with enough energy to hit the transition state. Okay. Now, if it's lower, more and more molecules can be in that transition state because you have enough energy in the system. Okay. So, and we can think of it as, you know, trying to put energy into our system is harder. It's like climbing upstairs versus getting there. And then you have your transition state, and, you know, I would stay there more than a transitory period if I took all day to hike up that mountain. But then it's easier to go down the other side to get to your products. And you've expended a lot of energy doing this, going all the way up the hill and all the way down the hill. You've expended a lot of energy doing this, okay? So let's talk about reaction rate, okay? So even if the reactions liberate the same amount of heat, going from reactants to products, right here, the higher the activation energy, the slower the reaction is going to go. So if you do something such that you have a very your species is reacting with something that is more, I don't want to say more reactive. If you're reacting with something that is already ready to react, you're going to have a low energy barrier, activation energy. And if you have something that has pretty stable bonds, but it needs a little more energy to get up that hill, so we'll have a slower rate. So just the height of that thing tells you something about the rate of the reaction, okay? But that's the first thing that tells you about the kinetics of reaction. The next thing that affects the kinetics of reaction is the concentration of the reactants, okay? So let's say you have only a few of each reactant. You're gonna have to wait a long time for them to have enough energy and be in the same place to form that transition state, right? So if you up the concentration, now you have twice as many molecules getting to that transition state at the same, at any one time, so the rate is faster. So the reaction rate increases with the increase of concentration. So because you have more molecules that can interact with each other. Okay. So that kind of makes sense, right? The higher concentration. Now there is a limitation. Once it gets so high, it changes the viscosity of the solution, then things go a little different. But just think of higher concentration, the higher the reaction. Right? Temperature also affects reaction, okay? Think about this, you know, if you're adding heat to the system, you're more likely to be able to get over that activation energy. That's the heat that you're using to get over that activation energy barrier. Therefore, increasing the temperature typically increases the rate. And the rule of thumb is that you can double the reaction rate by just increasing the temperature 10 degrees C. Okay, so that is really kind of interesting that, oh, I ran the reaction at 70 degrees and it took 2 days. I ran the reaction at 80 degrees and it took 1 day. And I ran the reaction at 90 degrees and it only took 12 hours. Okay, so that's what that effect of temperature does on your reaction rate. So the reason it does that is that you have more molecules with enough energy the higher temperature you go. Okay, so let's say we're starting the reaction at 50 degrees C right here. And you know, this is no energy, so that's the molecule that's just sitting there not moving at all in the solution, okay? It has no kinetic energy and it's just sitting there, okay? So there's no molecules to do that, okay? And so if you take the weighted average of all the energy of all the molecules, you know, that's gonna be about here. But notice that peak of energy for most of the molecules there is below the activation energy. So that means most of the molecules do not have enough energy to even begin to form that transition state, okay? So that means that as at this temperature here, all of these molecules, all the molecules under this curve do not have enough energy to form the transition state, okay? Only those few molecules right here under this curve here have enough energy to form that transition state. Therefore, only the ones that can form the transition state will go down and give us products. Okay. Now, by raising the temperature 10 degrees right here, our weighted average changes. Notice the 0 point is still the same because you can have less than 0 energy, but our weighted average shifts up. And when our weighted average shifts up, our activation energy did not change. But we now have more molecules that are in that range of having enough energy to form your activation, to form your transition state. More molecules forming transition state, faster you get the product. Okay? So that's the second thing that affects, no, it's the concentration, temperature, and the activation, the height of the activation energy. So that's the third thing that affects rate. Okay? The next thing that affects rate is steric hindrance. Okay? So imagine you have your transition state, you have to be forming a bond while breaking a bond, right? And let's say you have a big molecule that looks like an umbrella, okay? And you have to come in with your nucleophile to try to get opposite, it has to be 180 degrees from where the leaving group is, okay? So if you have a big umbrella shaped thing here and it's trying to come in here, you have to have a lot of energy to get it to even start forming that new bond so before it can start breaking that bond, okay? So let's say you take off half of that and it only has a stick sticking out now. You've taken off 2 of the other bonds here. So now this can come in a bunch of different ways. You only have one thing inhibiting it, okay? So the thing with less steric demand will have a faster reaction. The thing that has, you have to go in exactly at the right angle will be slower, okay? It doesn't matter how strong the nucleophile is, and if it can't get close enough to start forming that bond in the transition state, it slows the reaction down. Okay. So now that we know that the concentration affects it, we know that these different little things affect the rate, we need to figure out how to kind of quantify it for us so that we can figure out how fast or slow a reaction can go. So in this case, we're going to consider a substitution reaction. I said we'd call substitution reactions with an S right here. And we're going to do a nucleophilic substitution reaction where we have something with a negative charge coming in to make a new bond. And we're going to say that this is going to be one of those one-step reactions, right? That one-step reaction, it matters how much of a concentration you have on both of those because you need both of them to make your transition state, okay? So our SN2 reaction will probably only have one hump when we look at the energy diagram, okay? But because both of the components are necessary to make that transition state, the concentration of both are required in our rate law, okay? So our rate is the constant times the concentration of the substrate and the concentration of the nucleophile. Do we see why both of the concentration of the nucleophile and the substrate are required to form? Because we have them both there to make that transition state. If we didn't, if it formed an intermediate, we would only need the concentration of whatever's forming the intermediate because it breaks a bond first. Okay, and we'll see that in one of these other equations. Okay, so how does this relate to activation energy? Okay, we know that rate is affected by activation energy, but we also know it's affected by temperature, right? And steric demand. So we actually can count back out the activation energy by using the Arrhenius equation. Okay, don't worry, I'm not going to make you calculate. Okay, but we can take the rate constant of a reaction, and that's a measured thing, right? We're measuring the rate. That reaction constant is the K we calculated from the previous slide, and we monitor the concentration of the 2 reactants, the reactant and the nucleophile, right? We monitor those. That gives us this number here. Okay, now. This frequency factor or pre-exponential factor is also controlled by the type of reaction we have. Then we have E, that's the opposite of natural log, the activation energy, the rate law, I'm sorry, the ideal gas constant, and temperature in Kelvin. Okay. Good. What's a nucleophile and where do we find them? Okay, that's toward the end of this talk. So keep that in mind. We're going to talk about that today. Okay, so ideally what we can see here is if we change the temperature, we can increase the rate. If we have a high activation energy, we decrease the rate because this is an exponential part of E here. So that's where the activation energy can be measured by measuring the rate constant and the rate of the reaction. And this is why temperature increasing speeds up the reaction and activation increasing slows down the reaction because one's on the numerator, which makes it bigger and bigger. One's on the denominator, which makes it smaller and smaller. So that's why those are there. Okay, but the fact is that we can actually calculate that activation energy. It's not just some, oh, I think it's 5, you know, so we can actually calculate that. Okay, so the next thing that can affect the rate of the reaction is to use a catalyst, okay? So in the case of a catalyst, what you're doing is you're actually having it either interact with the catalyst to lower that activation energy, change the mechanistic pathway. For example, instead of having your reaction where it breaks apart and then waits around and has a nucleophile attack it, it binds to a metal, and then the metal binds to something else, and then it kind of spits both of them out with a new bond, okay? So that's what a catalyst would do in the system. It lowers this activation, this initial activation energy. Even though it goes through a couple different transitions, you still end up with the same products. So that's the effect of a catalyst on rate. Not only does it change the actual mechanism of the system, but you end up with the same products by lowering the activation energy. So the individual steps of the mechanism are different, but the net result of the reaction is the same. Okay, so that brings us up to the Hammock posture, okay? So if a reaction is exothermic, okay? If a reaction is exothermic, it means the transition state looks more like the starting materials. Okay, okay. Exothermic looks more like the starting materials. Okay, what does this mean? What this means is that if we looked at that transition state, the bond it's breaking is going to be shorter than the bond that is forming in the transition state, okay? Because this bond was stronger because we're giving off energy, right? So that stronger bond is going to be shorter than the new incoming bond form. And when this bond breaks, that stronger bond breaks, we end up giving off heat. So exothermic reactions look more like the starting material at the transition state because of that stronger bond. In contrast, if we have an endothermic reaction, that bond is the weaker bond. Our starting bond is the weaker bond. So it's going to start to break before it's going to be longer in that transition state than the new bond forming because that new bond forming is stronger and you're storing more energy, okay? So this is an interesting way to look at an endothermic and exothermic as then look at just the ideal situation within the transition states, okay? So that kind of helps you kind of decide, ooh, is it going to go forward or do I have to put a lot of energy to make it happen? Okay, so questions on kinetics, okay? Now, the other thing about this is so if you had a catalyst and a high temperature, your reaction would be very quick. Yes, they are additive. They're, you know, the temperature will affect it this much, the concentration will affect it this much, and the catalyst will affect it this much. So you can take a reaction that took 2 days and you can make it happen in 10 minutes. So it is theoretically possible. Okay, so we talked about thermodynamics, and that's all about storing energy or releasing energy from the bonds you formed. And kinetics is all about how fast the reaction is, okay? But they can compete in a reaction. So I'm going to teach you some things about how to see whether it's kinetically controlled or thermodynamically controlled, okay? So kinetics is all about the rate of the reaction and is most related to the height of the activation energy barrier, okay? The lower that barrier, the faster the reaction. No matter where the products end up, if this is a low barrier, you could have your products here, here, or here. Doesn't matter because it's going to happen faster, okay? In thermodynamics, it more approximates an equilibrium reaction where it'll keep going back and forth until the most stable product is formed, okay? So we think about equilibrium reactions where if you can go back and forth to starting materials and products, it's going to keep doing that until you form the most stable product, okay? Have the biggest release in free energy, have the biggest release in heat, okay? So even though we're both talking about energy, one's talking about the energy of the transition state, one's talking about the energy of the products, okay? So that being said, we can actually have a reaction that can be driven by its thermodynamics, or it can be driven by its kinetics. For example, in this first reaction here, this lower curve right here, reactant A and B are going to go through a transition state right here that leads to the production of two molecules, C and D, okay? And because it had a low activation energy, it was faster than the next reaction, the E2, the second reaction, the higher curve here. But the products it formed were different than the other reaction, and they had a lower energy in the end, okay? So because we had this activation energy, it formed these products. Let's say we ran the reaction at a higher temperature, so it had enough energy to get to this other transition state. So in this other transition state, that's a higher energy transition state, and it formed different products. And those different products were not as thermodynamically stable as the two products from this. So what this means is this lower curve is kinetically favored because it has a smaller activation energy, but it's also thermodynamically favored because it has a bigger change in enthalpy. It released more heat. The upper curve here, it's red on my screen, and it might be on yours. We went through a different transition state. We had a higher energy of activation, so it was a slower reaction, okay? Which one releases more heat? The one that's further down, furthest away from the starting materials releases more heat than the one that's not as far away from the starting materials. So in this one, we added heat. It went to a different transition state. It made different products, and these different products have a less of a difference in potential energy than the starting materials. So that means this reaction is kinetically unfavored and thermodynamically unfavored. It took more energy to get to the transition state, and it produced less stable products. So of the two reactions, this is both kinetically and thermodynamically favored, okay? But if you heated it up too much, trying to speed the reaction up, you're gonna get this one right here, and you're gonna get impurities. It might not be the most stable, it might not be the product you wanted, okay? So there's a balance between the heat and you can't heat the reaction too much or you'll get byproducts. And this is why you get those byproducts, because you're making it go through a different transition state. Okay, so both the lower curve is thermodynamically and kinetically favored compared to the red curve. Okay, so
Ian,
oh, go ahead.
So E and F are the weaker products?
E and F are the products with less heat released. They are closer to the starting materials, therefore less heat was released, so they're the less stable products, okay? So think of anything below the starting material, it's going to be thermodynamically favored, and the more heat released, even the more favored it is, okay? Does that make sense?
Yes, thank you.
Okay, so let's look at different curves. Okay, we're going to start with the same two reactants. We're going to heat them up at different rates, and we're going to see what happens here. So in this one right here, we're going to look at the top line first. We have a lot of heat we added to it. We got to one transition state. This one transition state that we had to add a lot of heat to gave us our products that were lower in potential energy, meaning they released heat more, meaning they're more thermodynamically stable. Okay, but we had a big activation energy. That means this is kinetically not favored, but thermodynamically favored because we gave off more heat, okay? It took more heat to get to transition state, but it gave us a more stable product, okay? So this is kinetically not favored, thermodynamically favored. So when you think about that, you want to think about a equilibrium reaction where you added a lot of heat and you're waiting for it to get to the thing. Now, it's possible for these two reactants to hit a different transition state at a lower energy. So kinetically, they would prefer to be at this lower energy, but the products they produce are not as thermodynamically stable. So that means this activation energy is kinetically favored, but it's thermodynamically unfavored from the product standpoint. Okay, so just looking at your curves and looking at the height of the activation energy and the amount of heat given off, you can see whether it's thermodynamically controlled or kinetically controlled. Okay, does that make sense? Okay. So I like that it's all visual. You don't have to remember pluses and minuses and greater than 0 and not 0. Look at the reaction diagram. It tells you all of that information. Okay. So what that means for us is the rate of formation of the most stable product will be faster than the formation of the less stable product, because the more stable product follows the pathway that is more stable. Lower activation energy state will have a smaller free energy activation, or a lower activation, the activation energy. So think about the height of that activation energy. If it's low, it's kinetically favored. Look at the products. The one that released the most heat is the thermodynamically favored. Okay. Let's see, what's the next slide here? All right. So what that means is, in those same reaction diagrams, if you ran a reaction at the lower temperature, okay, the molecules would not have enough energy to go to that second transition state, that higher energy transition state. That means that all of the reactions are going to go through the lower activation energy and form that product, okay? If you have that difference in energy is good enough that you can run the reaction at a lower temperature, it is kinetically controlled because it must use the lower energy activation barrier. Remember, activation energy is the kinetics part. The heat released is the thermodynamic part. If you run it at higher temperatures, or there's enough equilibrium in the reaction such that it'll keep going until the most heat is released in the products, then we have a thermodynamically controlled reaction. If you form the most stable products, you have a thermodynamically controlled reaction. Okay. Now, in the case of the diagrams I showed there, the activation energy was higher. It was not the kinetically favored one, but the products were favored. And if there's enough of an equilibrium for them to go back and forth, back and forth, back and forth, they're always going to try to find the lowest energy products possible. Okay, and that's what we call thermodynamic control. Questions on kinetic control versus thermodynamic control? Okay. Again, look at the activation energy for kinetics. Look at the product energy for thermodynamics.
So just to confirm, when you're looking at the thermodynamic control, you want the products to be lower, the lowest location from the starting.
You want the lowest activation energy barrier. You want this right here. The lower this is, the number one, the faster it goes, and the more likely it is to go to that transition state at lower temperatures. But if you have this reaction competing and then you heat it up really high, now you have enough energy to do this. And so you're going to do some of this, but you're also going to do some of this. And then that is a slower reaction, but gives you more stable products. Okay?
Yes, thank you.
All right. So if it's a slower reaction, but more stable products, it's thermodynamically controlled. If it's a faster reaction with less stable products, it's kinetically controlled. Okay, so we had a question there. What's a nucleophile and how do we find them? That's what we're going to talk about now, okay? So we're going to talk about acid-base reactions. So this is the type of reaction where we typically have a Lewis acid, which is willing to accept electrons to form a new sigma bond. And we have a Lewis base, which has electrons it's willing to share to form a new selective bond. So that's what we're going to look at. That's why we talked about acids and bases. And that's why I talked about it in that specific format, okay? Because we can use that to define what we call nucleophiles and electrophiles, okay? A nucleophile is something looking for or liking a positive charge, okay? So think Lewis base. I have electrons, I have a negative charge, I want to share them to make a new bond. I am a nucleophile, okay? Look for negative charges and lone pairs. Nucleophiles usually have one of those two things on it, okay? So it has electrons, it's willing to share, it's a nucleophile. Which means by contrast, if you have either a positive charge or less electrons than you want, you're looking to accept those electrons. And you're the electrophile. You're looking for electrons. And if, you know, well, nobody's old enough to know looking for electrons in all the wrong places. Sorry, that's from the 80s, I guess. And anyway, so when you have your electrophile, think Lewis acids, okay? Things with positive charge, things that are electron deficient. For example, things like, you know, positive, hydrogen and positive charges are things that you really want there, okay? A good example of electrophile is an alkyl halide, okay? Why? Because of bond polarity, okay? We have bond polarity here. The bond is pulling electron density toward the fluorine, making the carbon partially positive. That's why it's electron deficient. That's why it is an electrophile, because it's got that partial positive charge. Now a nucleophile can come in with its electrons to try to make a new bond. So nucleophiles are looking to form a new bond with the electrons they already have. Electrons are looking to form a new bond with somebody else's electrons. So I think that answers your question in the chapter. Okay, what are we looking at? 1:30. Okay, yeah, we got some time. All right, so let's look at some common ones. Okay, you'll start to recognize these really, really fast. And again, look for bond polarity in the system. Bond polarity tells you a lot about whether it's a nucleophile or an electrophile. Okay, so in the case of nucleophilic sites, we want to look for things that have more electron density or are having more of the electron density being dumped to it by a polar bond. In the case of this bond here, we have lithium and we have carbon. Carbon is actually has a higher nucleophilicity than lithium does. Because it has a higher nucleophilicity, it's going to pull electron density away from that lithium, making it a partially negative charge. So it is looking for positive charge because it has more electron density than just a non-polar bond would have. So look for polar bonds. Which way is that polarity going? Okay. Now, another nucleophilic site is if you already have a pair of electrons in a lone pair. Okay. Think Lewis base. Remember, those electrons could accept a proton on on water to make that hydronium ion, or accept a proton on there. So look for lone pairs. That's another great place. Okay. The next great nucleophilic site is the pi bond. Okay. And if you think about it, those pi bonds are the electrons in the p orbital. They're above and below the plane. They're not in between the two nuclei. They are above and below the plane of those two nuclei. They are out there in the open. They are ready to bond with something else. So that's another classical nucleophilic site. Okay. It has the electrons to go and react with. So this is the kind of thing where we have those addition reactions. They're addition reactions because that lone pair, that pi bond is a nucleophilic site. Okay. So in contrast, when we're looking for electrophilic sites, we're looking for a positive charge. And again, bond polarity can play. In the case of the carbon fluorine, that carbon is partially positive, this is partially negative, meaning that we can have an electrophile come in, a nucleophile come in and attack it and form a new bond. The other thing we can have is a positive charge. So in the case of a carbocation, we actually have an empty p orbital. It's ready to accept any electrons and all electrons it can, and therefore it's an electrophilic site, right? The other thing we can have is actually have something like boron. Boron is one of those weird ones that only bonds 3 times, okay? But it does have an empty p orbital, okay? And that empty p orbital will accept electrons to form a new bond. So we're looking for an electron deficient atom, okay? So notice carbon is a decent electrophilic site and boron are decent electrophilic sites, okay? Think the less nucleophilic atoms, like carbon, boron, and occasionally nitrogen. Those can all act as that. So looking for a positive charge, looking for a polar bond. Okay, so now we know what nucleophiles are by definition and electrophiles by our definition, and we have a really good way to kind of look for them in any reaction, okay? So what I want you to do is to start looking at every single molecule and say, ooh, where's the polar bond? Ooh, is it positive or negative? Is this going to be the electrophile or nucleophile? If you just spontaneously start doing that, every time I throw a reagent at you, you're going to start to say, oh, that's probably going to react this way. Or, oh, that's going to react that way. You're going to start to see the pattern. This pattern of acid-base happens over and over and over again in most of our mechanisms. Okay, so that being said, let's talk about what a mechanism is and how we use it, okay? Mechanisms are basically a hand-waving way of saying what's happening in each step of the reaction, okay? There has to be a reason for this to happen, right? So we can't just say, oh, it just wanted to be trigonal planar for some reason. No, there's a reason for it. And the way we explain it is we push electrons around. We show our Lewis dot structure saying, oh, well, it has extra electrons. I'm gonna push those electrons over here and make a bond. Or it doesn't have electrons. I'm gonna put some electrons here. So we're gonna use this electron pushing step to show you which way reactions are gonna go. And you're gonna see this happen again and again. The electrons that are forming the bond typically are coming from your nucleophile. Your electrons that are the atom that's accepting the electrons is typically your electrophile. Okay, so what does that look like? Okay, so when we do this, we have a specific nomenclature where we draw an arrow with two barbs on it. Okay, now we draw it with two barbs to show you that you have two electrons coming into this. Okay, in chapter 10, we're going to show you an arrow with one electron. Okay, and that's going to have one barb on it. Okay, so one barb means one electron, two barbs means two electrons. So get that in your head. Always use the two barbs in this next chapter right here. Okay, that being said, we're taking the electrons from the electrophile, we're extending them into the nucleophile, and those are the electrons that make that new sigma bond. Okay, so we've shown it step by step saying these are the electrons we're going to use to make this new bond by pushing the electrons around with that arrow. Okay. All right. Does that make sense? Okay. So this is a very common in a single step nucleophilic attack where the electrons just form that new bond. Okay. Now, sometimes you have to go in two steps because it's not, it has to add something and then you have to do something else. Or sometimes you form an intermediate like a carbocation or something like that. So sometimes it happens in two steps, okay? So in this case here, what we're gonna do is we're gonna start with our nucleophile here. It has a negative charge. We should immediately think nucleophile, okay? Or Lewis base, right? Now, this one's not as easy to think about. Okay, wait, what side is the electrophile? Oh, wait, hold it. We have an oxygen and a carbon. Oxygen is more nucleophilic, it has higher nucleophilicity, so it's pulling electron density away from that carbon, right? So we have a polar bond here. Even though it's a double bond, it's a polar bond, making this carbon partially positive. That's how we recognize where it's going to attack, okay? We look for that bond polarity. Now, our electrons are going to come in and start to attack our system here, but we can't have 5 bonds to carbon. So what happens? We break the pi bond and we put the charge on the oxygen up here. Okay, so that's the first step, okay? Notice we started with a neutral species and a negative species, and we're ended up with a negative species still, okay? That means that something else has to happen. We have to get rid of that negative charge to get to our neutral species. And in that case, we would have to do a second attack. A second thing has to happen, okay? All right, so in here we formed this reactive intermediate right here, that it's got to do something else to go back and become neutral. Okay. Again, we cannot have 10 electrons around carbon, no 5 bonds to carbon. So the way we accomplish that is we take that pi bond, break it, and leave those electrons on the most nucleophilic atom. The one that wants the electrons is where that negative charge is going to lie. Okay. So then the next thing, something else has to happen to make this species go forward. But that's how we do it in that step. Okay. Now, we are going to do pushing of electrons to break a bond, okay? So we're not having electrons come in to form a new bond. We're actually having electrons leave to break a bond, okay? And again, the electrons always leave with a more nucleophilic atom, okay? Bromine is more nucleophilic than carbon. Therefore, both electrons are going to go with the bromine, double barbed arrow, to give us a Lewis base and to give us a carbocation, which is our Lewis acid. Now remember, this is heterolytic cleavage. We're leaving with a negative charge on one and a positive charge on the other. So we have a heterolytic cleavage, different. So that's another thing that can happen. But again, it's the same thing. We're pushing electrons from the less nucleophilic species to the more nucleophilic species. Okay, come on, all right. So another thing that can happen in a mechanism, besides having a nucleophilic attack, besides having a substitution, besides having an addition, we can also do what we call a proton transfer, okay? And in the case here, we have something with lone pairs on it. It can be neutral, and it will reach out and grab a hydrogen. When it does that, we do it in a couple of different steps, okay? The first thing we have is the lone pair from the species that's gonna take the hydrogen. That lone pair has to come out and start forming the bond with the hydrogen. That means that hydrogen does not need the 2 electrons that it currently has with the bond of the molecule it's already on. So it leaves those behind, okay? So in that proton transfer, we're leaving those electrons behind, giving us our neutral species again. And now we have our charged species here, okay? And when we calculate the formal charge, because there's not a formal charge on hydrogen, that positive charge resides on oxygen. Now, that's not the best place for that positive charge to be because it's the more electrophilic atom, but it does happen. So the other thing we can have happen is we can deprotonate an oxonium ion. So the oxonium ion is when you have either an alcohol or just like water, instead of being hydronium ion, it's actually made with an alcohol. We took one of the lone pairs off of the oxygen on the alcohol and we added a hydrogen to it, giving us a positive charge on oxygen. Okay. Now, we can have anything come over that is more basic than that system, and it's going to be something like an electrophile. It's going to have electrons. It's going to reach out, grab that, liberating our alcohol, making it into a neutral species, and forming our new sigma bond. So follow the electrons, okay? The electrons are all the bonds are in the electrons, follow the electrons. Okay, so let's see, we have enough time to introduce carbocations. So I said one of those things that was a Lewis acid, one of those things that was an electrophile was a positively charged carbon, and I called it a carbocation. So let's talk about carbocations. Think about it. It's carbon with a positive charge, carbocation, okay? So we have different classifications of carbocations, and then we have what we call a primary carbocation, which means it has one other thing attached to it, usually carbon, okay? So that gives us only one thing for it to have, one thing other than hydrogen, I gotta say, one thing other than hydrogen is a primary. If it has 2 things other than hydrogen, it's a secondary. If it has 3 substituents, it has what we call a tertiary carbocation. You cannot have a quaternary carbocation because then you have 4 things bonded to it and carbon's happy. So we only have primary, secondary, and tertiary. And occasionally we call the methyl cation. That's a unique one, but we don't use it. But anyway. All right, so let's talk about those. We have the least stable is what we call this methyl cation here. And it's technically not a primary, but it has only 3 hydrogens on it here. This is our primary, and this is our secondary. Notice that one thing other than hydrogen on it. This has 2 other things than hydrogen on it. And if we look at the last one, we have 3 other things than hydrogen on it, giving us our tertiary carbocation. So if we just were to go in the lab and play with these things, we would find out that this methyl one is very unstable, very hard to make. This primary one is a little more stable, but still very hard to make. The secondary one, well, we can make it sometimes. And the tertiary one is really easy to make, okay? So just from that kind of experimentation, we would say that the tertiary carbocation is the most stable because it's the easiest to make, followed by the secondary, primary, and methyl group. But why? Why do we care? Well, we care because that's going to be which one's going to be more likely to use in a reaction. But why does it happen? Okay. Okay. It happens because if you have groups attached to that positively charged carbon that can donate electron density either through the bond inductively or by hyperconjugation through a space interaction to stabilize that positive charge, it is more stable. Imagine you have 3 hydrogens there, okay? The hydrogen has no extra electrons to share, right? It only has the 2 that's using to make the signal bond. But you have a carbon and it's got 3 other bonds that it can pull a little bit of electron density through and give it to that positively charged carbon. So that's the inductive effect we're going to look at. And that helps it because each little bit you give to that positive charge makes it a little less positive, which makes it more stable. The second thing we have is hyperconjugation. That's where it can donate electron density from the clouds of electrons around the hydrogens through space to help balance that charge. Okay. So let's look at it from the inductive effect first, okay? So if we have our methyl group here, we have only the electrons that are already used to make our bonds here to help stabilize that positive charge. So it is a very hard, very positive, it almost has 100% of its charge available there because it can't suck away electrons from anywhere else. Okay. By just adding that one methyl group, okay, that one methyl group can donate some of its electron density, making it only about 90% of a positive charge. Just relatively, I'm just saying that it doesn't have to carry that full positive charge on that one atom. It can now have just 90% of that positive charge character because it's pulling those electrons. Now, what if you have 2 on there? Well, gosh, you can do the one both atoms, and they're going to donate a little bit differently. And so, you know, we're only going to have 80% of a positive charge. Okay, so that's, you know, the numbers are just a relativistic thing. It's just showing you that there is, every time you add a group, there's extra donation, making it more and more stable. And by the time you get to 3, you can do that, all of them. And that gives you, you know, relatively 70% of that. Now, also, in this position here, you can see that the hydrogens are positioned in a way that they can donate through space to that center carbon, because the positive charge of this carbocation is actually in an empty p orbital above and below the plane of our carbocation. And so through space, they're dumping into that empty p orbital to help stabilize it as well. That's the hyperconjugation effect. If it's pulling it directly through the bonds, that's the inductive effect. Okay, so because there's such a difference in stability between the primary, secondary, and tertiary, it's prone to rearrangement. I told you one of those reaction types we have is a rearrangement reaction. This is one of the first ones we're going to talk about. Whenever you have a secondary carbocation, it's not as stable as a tertiary carbocation. So carbocations tend to rearrange to make the most stable carbocation possible. Okay, so what's going to happen is you typically go from a secondary to a tertiary, but it only shifts 1 carbon. You're not going to take a carbocation on this side of the molecule and move it over here. It's going to shift 1 carbon and 1 carbon only. It goes from a secondary to a tertiary. Okay, and it can do it 2 ways. We can do it by doing what we call a 1-2 hydride shift. Now it's a hydride shift because the electron's moving both of the electrons that were at sigma bond over 1 atom. So we have 1 carbon that had the carbocation, 1 carbon had the hydrogen on it, which is the 2 carbon, and then it shifts over that 1 position. It only does it to form the more stable carbocation. For example, actually I have a drawing of it here. Okay, or you can even do it with a methyl group. Okay, The only other thing you'll move besides a hydride and a methyl group are if you have a ring, it'll move one of those methylenes to make a bigger and bigger ring. But think of only moving a hydrogen to make that tertiary carbocation, or moving a methyl group to make that tertiary carbocation. So what does that look like? Okay, so let's say we had an alkyl halide and we heated it up and we had homolytic cleavage, okay? I'm sorry, heterolytic cleavage, and we formed a bromide ion and a carbocation, okay? And it was a secondary alkyl bromide, and we saw that it gave us this secondary carbocation first, okay? The carbon next to it has two things attached to it and would form a tertiary carbocation. So to make it more stable, it's going to take both electrons from the sigma bond of hydrogen, move it over one carbon and one carbon only to make the more stable tertiary carbocation. Okay. So think it's almost always going to happen within a secondary and a tertiary. It's always going to form that tertiary carbocation. But what if you don't have a methyl group of hydrogen available to you like you do here? Okay, well, in that case, you take both electrons from that sigma bond, move them over one carbon to form your tertiary carbocation. Notice if you moved this hydrogen over here, it would reform a tertiary carbocation here, but that doesn't happen. You already have a stable tertiary carbocation. You already have a stable tertiary carbocation, so it's only going to go once. It's only going to go from a secondary to a tertiary. It does not exchange to a tertiary to a tertiary. So only do it once, okay? All right, so we want it to be more stable, and it will do it with this hydride shift or this methyl shift. Okay, and let me see what my next slide is. Okay, I'm gonna not do bond energy yet. Okay, we got about 3 minutes left. So one of the things we want to, the other thing I want to talk about actually before we go too far away from the carbocation is I want to show you the structure of it. Okay, so we have a carbon in the middle, and this carbon is actually sp2 hybridized, and it's got three things attached to it, and these are three sigma bonds, right? And so all of these are your sp2 hybridized orbitals, so it's trigonal planar. Okay, so let me take it that way. That looks like a bond. Okay, so structurally it's trigonal planar, which means it's 120 degrees apart and flat, okay? But where's the other P? Okay, I said the other P is empty orbital above and below the plane created by the sp2 hybridized carbon, okay? Because it's above and below the plane and it's empty, that gives rise to, if we have a carbon with a hydrogen here, that hydrogen has some electron density that it can donate through space to help stabilize that tertiary carbocation. And that's the hyperconjugation effect. Going straight through the bond, the sigma bond, is the inductive effect. But it's really important to imagine a carbocation as a trigonal planar structure with an empty p orbital above and below the plane, because it'll give us an idea that our products are going to be related to the structure of this intermediate. Okay, so questions about any of the things today? Okay, well, if you don't have any questions, let me go ahead, and have a safe spring break. You know, travel if you can, but be safe if you can. Come back to us healthy, please. And I mean, I know we're all online anyway, but still come back to us healthy and ready to go. Note your homework for chapter 5 is due the Monday after you get back from spring break on the 22nd, okay? I didn't have it due over spring break, and the homework for this chapter isn't due till the following week, because we're gonna have 2 more lectures on this next week, maybe 3, and we'll be able to finish up chapter 6 at that time, okay? So have a safe and fun spring break, or just get caught up on all your homework if you're staying in town. You know, I'm going to get caught up on a lot of stuff and hopefully care for a lot of people and have a nice, safe break myself. All right.
Thank you.
I'm going to go ahead and stop recording and stop sharing.